Dear students, welcome to the next lecture of Inorganic Chemistry. In this lecture, we shall continue with our discussion on Group 15 elements. The elements of Group 15 form binary hydrides of the general formula EH3, and the simplest binary hydride is ammonia, NH3, then PH3 phosphine. Arsenic hydride is arsine, AsH3. Stibine is SbH3 and bismuthine BiH3. The hydrides of group 15 elements are gases at room temperature and they are water soluble. PH3, AsH3 and SbH3 are poisonous and the hydride of bismuth is unstable. The hydrides of group 15 elements have pyramidal structure. We are very familiar with the structure of ammonia with nitrogen in sp3 hybridized state. The three hybridized orbitals overlap with the 1s atomic orbital of hydrogen and one sp3 hybridized orbital contains the lone pair of electrons. Similarly, all the hydrides have pyramidal shape. The bond angle is lower than that of the tetrahedral angle because the lone pair bond pair repulsion is greater than the bond pair repulsion. And as we move down the group, the bond angle decreases. The bond angle of ammonia is 107 degree and it decreases to 90.4 in the case of BiH3. This can be explained on the basis of the increase in atomic size. As we go down the group, the atomic size increases and electronegativity decreases. And thus the bond pair repulsion decreases and hence the bond angle also decreases as we move down the group from ammonia to bismuth. If we compare the boiling points of the hydrides, we can see that the boiling point increases from pH3 to BiH3. It is shown in the graph and this can be explained on the basis of increase in molecular size. From phosphorus to bismuth, as we move down the group, the molecular size increases and hence the van der Waals forces increases and thus the boiling point of the corresponding hydride increases. From the graph, it is very clear that ammonia shows an anomalous high boiling point. This is because nitrogen is a highly electronegative atom. The electronegativity of nitrogen is 3 and that of hydrogen is 2.1. The difference between the electronegativity of nitrogen and hydrogen makes the NH bond polar. And thus there is a possibility of intermolecular hydrogen bonding in ammonia. Due to this intermolecular hydrogen bonding, ammonia shows a very high boiling point compared to that of the next member, phosphorus hydride. The electronegativity of phosphorus is very close to that of hydrogen, so that pH bond is not polar and there is no possibility of intermolecular hydrogen bonding in phosphorus hydride. Thus, the boiling point of ammonia is higher than that of pH3. As we move down the group from nitrogen to bismuth, the atomic size increases. As the atomic size increases, the effective overlap with the 1s orbital of hydrogen decreases, and hence the bond strength decreases from nitrogen to bismuth. That is, the NH bond is stronger compared to that of PH bond, which is again stronger than ASH bond, which is again stronger than SBH bond, and BIH bond is the one with least bond strength. And as the bond strength decreases, the thermal stability of the molecule decreases from NH3 to BiH3. And the decrease in thermal stability causes an increase in the reducing character. Thus, BiH3 is the strongest reducing agent among the hydrides of group 15. The BiH bond is less stable and hydrogen can be easily released, so that it has the strongest reducing character. Due to the presence of lone pair on the central atom, the hydrides of group 15 elements are Lewis bases. If we compare the basicity of these hydrides, it is found that ammonia is the most basic binary hydride of group 15 elements. This can be explained as follows. As we move down the group from nitrogen to bismuth, the atomic size increases. As the atomic size increases, the lone pair of electrons on the central atom gets more diffused. This causes a decrease in the donor capacity of the hydride. As the donor capacity of the hydride decreases, the basicity decreases. Thus, ammonia molecule in which nitrogen is of comparably low size has the highest Lewis basicity, and bismuth hydride has the lowest basicity value. The group 15 elements form oxides of the general formula E2O3 and E2O5. The acidic character of these oxides decreases down the group. Comparing E2O3 and E2O5, E2O5 molecule is more acidic than E2O3 in all the cases. Nitrogen forms several oxides in which the oxidation state of nitrogen varies from +1 to +5. We shall discuss the oxides of nitrogen. The first one is dinitrogen monoxide or nitrous oxide. It is commonly known as laughing gas. The oxidation state of nitrogen in dinitrogen monoxide is +1. The molecule is diamagnetic and it has a linear shape. It is soluble in water. At room temperature, the laughing gas is a colorless, non-flammable gas with a slight metallic scent. And at elevated temperature, It is a powerful oxidizer. Next one is nitrogen monoxide, in which the oxidation state of nitrogen is plus 2. This molecule is otherwise called nitric oxide. It has an unpaired electron and thus nitric oxide is paramagnetic. It is a colorless gas. Next one is dinitrogen trioxide. It is a blue solid or liquid at extremely low temperatures. It dissociates into NO and NO2, which is a reversible reaction. The molecule is planar. The electrons are paired and it is diamagnetic in nature. In this molecule, the oxidation state of nitrogen is plus 3. Next comes NO2, nitrogen dioxide, which is a brown gas. NO2 reversibly dimerizes into N2O4. NO2 exists in two resonance forms. The molecule is paramagnetic and planar. The oxidation state of nitrogen is plus 4 in nitrogen dioxide. The dimeric form of nitrogen dioxide is dinitrogen tetroxide or N2O4. It is diamagnetic and colorless. N2O4 has two resonance structures as shown in the figure. The next oxide is dinitrogen pentoxide, which is also known as nitric anhydride. This molecule is diamagnetic in nature and a colorless solid. The oxidation state of nitrogen in dinitrogen pentoxide is plus 5. This molecule also exists in two resonance forms. Next comes the oxides of phosphorus. The first one is P4O6. It is also known as phosphorus anhydride. The structure of P4O6 is given here. All the PO bond length are same. It is 166 picometer. All the oxygens are bridging oxygens which connects two phosphorus atoms. The oxidation state of phosphorus in P4O6 is plus 3. The molecule is a colorless volatile solid. Next is P4O10. This is called phosphoric anhydride, in which the oxidation state of phosphorus is plus 5. The molecule is a white deliquescent solid. In P4O10, there are two types of oxygens, bridging oxygens as well as terminal oxygens. The structure of the molecule is shown in the figure. Apart from P4O6 and P4O10, there are other oxides of phosphorus, P4O7, P4O8 and P4O9. In these three oxides, the oxidation state of phosphorus is plus 3 and plus 5. The phosphorus atoms to which terminal oxygens are attached have an oxidation state of plus 5, and to those to which only bridging oxygens are attached will have an oxidation state of plus 3. In P4O7 there is one terminal oxygen. P4O8 there are two terminal oxygens, and P4O9 there are three terminal oxygens. So in P4O9 the three phosphorus atoms to which terminal oxygens are attached will show plus 5 oxidation state, and the last phosphorus atom to which only bridging oxygens are attached will have an oxidation state of plus 3. These are the oxides of nitrogen and phosphorus.